from the concept of the lower section, and we draw the free body diagram in the first video with the lower section. And let's continue with some math in here. So let's use the volume method. So let's talk about the by volume method on the lower section that we just draw. So with that, as you can see, the sum of all the force in the left hand side due to the normal stress distributed in that portion is equal to volume. So you have to take the integral sum of all the force at the left hand side is equal to the stress, normal stress at the left hand side time the areas. So if we work on any areas that you deal with here, that portion areas, and that is dA in this case, to differentiate with the A for the whole cross section, we only deal with the lower section. I call that a dA apostrophe. And where is the integral from where to where? Because we cut from the position Y. And if we have C, if you call C is from the neutral axis to outermost fiber, and you already know that is C. Right? That in the bending moment. C is from the neutral axis to outermost fiber. Then for this left hand side, and you can see they will go from Y to C, to the outermost fiber. So with that, we can have it here. For the integral, it will go from Y to C, outermost fiber of that left hand side. And similarly, without any further complication, we also have the right hand side for the force is equal to sigma right hand side dA apostrophe, just one small on the cross section that the for the lower section that we do, and it's from Y to C for that with the volume method. And then as you can see, VH basically that the sum of all the force due to the shear stress on the plug surface that I cut with the position Y from the neutral axis. So that VH, how that VH is equal to, so you can have horizontal shear is equal to the areas times the shear stress. So shear stress, we already know that is tau, the areas of that surface in here, and you can see it's the rectangles equal to the width times the length. The width is the T, which is the thickness of the beam. And then we also have dx. So what is the thick or the width of the beam? T here, that is the width of the beam. And you can see that when I assume the cross section is a rectangle, so of course it can be any cross section that we will deal with later on. So that VH equal to tau, which is the shear stress times the width of the beam times the dx, the differential slice that we talking about. So let's make a few assumptions before we continue. So let's assume first we have 4 assumptions. The first one we assume is plane section remain plane, so it's no distortion, right? Plane. And then we have homogeneous, so same material throughout, and isotropic, same property prismatic, not isotropic, late prismatics. When it prismatics, it means that you see the cross section, the same geometry property. So for this two, we mean that it will be constant material and geometric properties in cross section, and geometric properties. Let's put all red here. Constant material and geometric properties throughout cross section, in the cross section that we talking about. And the last one is linear elastic, so that we can apply the normal stress equation from the bending moment. So it will be linear elastic. So what does that mean? We will have the sigma equal to my over I. So that's what we have. So with that assumption, what do I have here? With that assumption, what do I have? Sigma left hand side, because linear elastic, so sigma left hand side, that is the normal stress due to moment, it equal to my, the internal bending moment in the left, divided by the I. And because it's prismatic, so it's same geometry through the cross section. So you have the moment on the left, so it will be my over I for the left hand side. And of course, you also do the same. We have sigma right hand side, it equal to the moment on the right hand side, the internal bending moment, m plus dm, that you have that y divided by I. So that is the bending moment equation that we already learned from here, right? M plus dm for the normal stress. So if we plug that into force left hand side equation, what do I have? The force in left hand side equal to integral, right? Integral sigma left hand side d a. So let's do it there. Y to c sigma left hand side m y over I, and then we have it d a apostrophe. And as you can see at that cross section, the m is constant, the internal force when the load everything applied, same support, then m is constant. At that cross section, I, because prismatic, I the same. At that cross section, I can print out, so it will be m over I y to c y d a apostrophe. Similarly, with the force due to the at the right hand side, also yc, and in this case for the sigma right hand side, plug in m plus dm over I y d a apostrophe. Also print out, I also have m over I y over c y d a apostrophe plus dm over I y to c y d a apostrophe. So from that, what do we have? Plug in the equation, and you can see from the force in the left hand side equal to VH right hand side. So from that one, I can also have, from this, I can also have the VH equal to BH equal to what? Force due to at the right hand side minus force left hand side. From that equation, I plug 2 here with on the thing that I already have. So we have right now we have VH from the equation that I just showed you. VH equal to the force due to the from the right hand side, subtract the force for the left hand side. Something we have there, right? So plug in VH equal to tau T dx. So just plug in, we have it on the left, tau T dx equal to F right hand side, M over I YC YDA apostrophe plus DM over I YC YDA apostrophe minus force in the left hand side. It will be equal to M over I YC and we have YDA apostrophe. So plug that in. What do you have in here? What do you have in here? We can cancel out. Yes. Everyone see that? So from that we can have simplify the equation. I have tau T dx equal to dm over I YC YDA apostrophe. And if you recall from the just the previous lesson, the shear and moment diagram, if you recall, yes. If not, go back to see the note and the video there. If you recall, dm over dx. What is that? dm over dx. Do you recall? That the slope of the moment diagram. The slope of the moment diagram. And if you recall, when you draw the moment diagram, the slope of moment diagram, note number 4, equal to the magnitude of the shear. The magnitude of the shear. And the change in the moment equal to the area under the shear curve. On kind of that. It's here. Go back there, right? So there, that for the purpose. Go back to review that. And then you also let this portion. Let this portion here. This integral equal to, let that integral of y to c yd a apostrophe equal to q. What is q? We are going to define later. Just like before we have the integral and we put that the area moments of inertia or polar moment of inertia in torsion. So all of that we have it make it simplified with the symbol, and we define that later on. It do the same in here. Then what do I have from that equation here? Then if I have all of that and that record, then what I have here is from that equation tau T dx equal to dm over I. dm we know that is from here. We have v equal to v dx. Let's put down here. We have dm equal to v dx. So I plug that in that equation dm over I, so I can have that is v dx over I, because dm over I, dm equal to v dx, as you can see. And that integral y to c yda apostrophe, that already q, so I can write that here, q in here. So you can simplify the dx at both sides, and you can see there. So dx in both sides you can simplify, so you can have the final equation for the tau. So I simplify, divide, cancel dx, and I divide t going down in there. So I will have v q over it, and basically that's a critical equation for today. So I can say that that is the most critical equation for today. So that equation, we call that a transverse shear stress equation. Shear stress equation. So in the next video, we will explain the Q, what is Q in here, and then we go back to see how the transverse shear stress distributed throughout the cross section due to the shear V, as you can see in that equation.